Hey guys, welcome back. We're going to be starting the next chapter, chapter 14. This will be over the formal probability rules. This is one of the assignments we will be doing in class. We'll be doing this lecture in class. So if you're a B student, just work on the stuff from last week until Thursday. We'll do this one in class on Thursday. So, and if you're doing this at home, if you're a distance learning student, just let me know if you have any questions. All right, you can do it whenever you want. All right, so we're going to be moving into the formal rules behind probability. Today we'll look at the general multiplication and addition rule, which will allow us to add sets together even when they're not mutually exclusive, so if there's an overlap. And it'll also allow us to multiply two events even if they're not independent using conditional probability. I think probably the most important thing you'll learn will be conditional probability, and we'll be using those with tree diagrams later this week as well. All right, so we'll also be talking about college dorms and meal plans. So looked up a nice pretty picture so you have something to look at except for my face. All right, so the general addition rule. So this is what we can do when they're not mutually exclusive. When they're not mutually exclusive, that means they overlap. So for instance, students that live in the dorms or a meal plan, 56% of students live at a certain university live in the dorms, 62% have meal plans. It's interesting that more have meal plans than live in the dorms, and 42% are both. So there are some that live in the dorms that don't have meal plans, and there's some that have meal plans that don't live in the dorms, which is kind of cool. So normally before, when we wanted to know the probability of A or B occurring, so if you had a meal plan or lived in the dorm, we would have them when they were mutually exclusive and there was no overlap. For instance, like having type A blood or type B blood. Well, nobody can have both types of blood. You can't have AB, but that's not the same thing, right? And so they were mutually exclusive. You can't be a freshman and a sophomore at the same time, so we could just add them together. But now there's overlap, right? We can't just add dorms and meal plans. That would be 1.18. Well, we can't have a probability over 1, so we know there's something wrong. So how we correct for that is we add their probabilities together like we did before, but then we subtract the intersection between the two, which is the overlap. If you think about it, if we add the 56% plus the 62%, the 42% that were both got counted twice because they got counted among the people who lived in the dorms and among the people who lived in the meal plan. So we correct for it by just simply subtracting that intersection so that they're only counted once instead of being counted twice. So if we do that, we would get, let me grab the calculator real quick. I'll pull it up here. So we have 0.56 plus 0.62 minus the overlap, which is 0.42, which would be 76%. So we're saying that 76% of people lived in the dorms or lived or had a meal plan. So anyway, 56% plus 62 minus the 42 would be 76% altogether. So pretty simple. All right, the exclusive OR, we rarely ever use this one. It's usually an inclusive OR, and any time that somebody uses the word OR, it's implied that it is inclusive. So don't worry too much about the exclusive one, but I want to go ahead and show it to you. So when you want to know the union of two sets excluding the intersection, so for instance, if you're asked a question, would you like chicken or beef enchiladas? They're not asking if you want both. So do you want chicken in your enchiladas or do you want beef? I suppose you could get one of each or whatever, just depends. But there are times when we use the word OR, and it's implied that it's exclusive, okay? And that would be an example of it. So for instance, do you want to put on the soft tires or the all-terrain tires on your car? Well, you're not going to put both. It's going to be one or the other, right? So there are times, but most of the time it's going to be inclusive with probability. All right, so what's the probability that you stay in the dorms or you have a meal plan but not both? So we want to know just the people with dorms or just people in the meal plan. Well, the first thing you would notice is that the 0.56, I've had it where that was straddling the line. So that helped me, kind of giving me a visual clue that it was whenever we're creating our Venn diagrams. So we're talking about dorms, but also including the overlap. So the overall percent that were in the dorms or meal plan. And then for meal plan, the 0.62 straddle the line as well. So if I want to know the disjoint probability of only meal plan or only dorms, we just subtract the overlap from the overall dorms. So 56% stayed in the dorms, 42% overall were both. So we subtract the two, meaning 14% stayed in the dorms but did not have a meal plan. So the disjoint one. 62 minus 42 would be 20%. So 20% of students at the university had a meal plan but did not stay in the dorms. Now that we have the three disjoint probabilities, we could just add all three of those to find the union of those two, and then we wouldn't have to subtract one twice in the middle. Lots of different ways of doing this. But if we only wanted to know the two, the dorms or the meal plan, but not both. So the exclusive or, we could add the 14 and the 20%, or we could do the 56 plus the 62 minus 2 times the 1 in the middle. So that would look something like this. I'm just going to modify this. So 2 times 0.42. All right, so it should give me 34%, which it does. No problem. All right, let's see. So example 2. Records indicate 78% of drivers stopped on suspicion of drunk driving are given a breath test, 36% a blood test, and 22% are given both. Find the probability for a DWI suspect, given someone who was pulled over for that, basically, a suspected DWI, whatever. Given a test, the probability. Oh, so if they were tested or pulled over for suspicion, probability that they were given a breath or blood. So breath or blood, we'd add them together, but then again, we have to subtract the overlap because you could have been given both. On this one, if we wanted to, we could actually go ahead and find the other ones. So the disjoint probability, 78 minus 22 would give us 56, and then 38 minus 22 would give us 16. So another way we could, once we do that, if we're actually going to fill in the Venn diagram, then you could add all the disjoint probabilities together to get that same probability of breath or blood. So 78 plus 38 minus 22 would give us 94%. So 94% were tested with one or the other, breath or blood. Probability blood or breath, but not both. So this would be the exclusive. So now we're going to subtract the middle one twice. So it's going to be 22% less than that one, which would be 72. You could also do the 56%, the disjoint only breath, plus the 16% blood, only blood. That would give us 72% as well. Neither test. So once I know that the sum of those together, that they were tested, something was 94%, I could find the complement by just subtracting it from 1, which would give me 6%. Fairly simple. All right, conditional probability. This one's really, really important. So the probability of event B occurring knowing that A has already happened. And so this is annotated probability of B occurring given, is what we say when we have that line there. It's kind of like a parallel line or whatever. So B given A has already occurred. So the probability is calculated by the intersection of the two, so the probability of A and B occurring divided by the probability of A occurring. And we'll hopefully, as we get through this, you'll understand what's going on here. So the intersection is the and here. That's going to be the probability of A and B. So let's say we want to know what's the probability that you had A. I define this as A and B in this case. So we're going to read this again. So the probability that B, which is blood, so the probability that you're given a blood test given you had already been given a breath test. So first we want to find the intersection of both. So what probability have been both blood and breath? That would be 22%, okay? And then out of all the people that had both, which would be 0.78. Okay, so what we're doing here is we already know that A has happened, okay? So we don't care about this and we don't care about this, right? We're only just honing in on that 78%. So that's why it's our denominator. Out of the 78% that had been given breathalyzer test or whatever, what percent had been also given a blood test, which would be the 22%. So it's 22 out of the 78%, and that's the conditional probability of the likelihood of you being given a blood test if we already knew you had been given a breathalyzer test, which when I put that in the calculator, I get 28%. So conditional probability. Example 3, 2 psychologists surveyed 478 children. So we've got all the breakdown here. In grades 4, 5, and 6 in elementary schools in Michigan, and asked them their primary goal in school. They asked them whether it was grades, to be popular, or sports. I only care about one of those things. That's how I would have answered. Kind of funny. All right, probability. What's the probability that you were a girl, and so intersection, and you were most interested in being popular? So what's the probability a girl intersect with popular? So popular and girl intersection is going to be 91. So it would be 91 out of everyone, which would be 478. Okay, because it's not a conditional probability, it's just out of everybody. So out of all the people interviewed, what's the probability that you were a girl interested in being popular, which would be 19%. What's the probability out of everyone that you were interested in sports, or your primary goal, or one of your goals yeah, your primary goal, sorry, was sports. So it'd be 90 out of 478, which would be almost the same, right? Just a little bit less. 18.8%. What's the probability, this is a given one, so this is a conditional probability. What's the probability that your primary goal was sports given that you were a girl? So now our denominator is going to change. We're only interested in those that were girls, which would be 251. So out of the 251 girls that were interviewed, what percent of those were interested in sports? So now we're going to look at the intersection of those two. So not all the sports, but only the girls that were interested in sports, which would be 30. Remember, that's the intersection of those two. So 30 out of the 251 girls, which would give us 11.95. Now what's interesting is we can actually tell if these are independent if the probability of liking sports is the same as the probability of liking sports given that you're a girl. So this is really the marginal distribution. So 18.8% of all students like sports, and this is the conditional distribution, which is the 11.95%. Now these two would have to be the same or very, very close in order for us to say that there's no evidence or very little evidence of an association between these two. Now clearly there's an association if we look at the graphs of all these conditional distributions for the girls and the conditional distribution for the boys. They're not the same. So it looks like boys are much more likely to be interested or concerned with their primary goal being sports, and girls are much more concerned about being popular. And so since all these breakdowns and grades were actually about even between the two, so it's really just between popularity and sports between the differences between these boys and these girls. All right, and so we would say there would be evidence of an association, and you will want to be able to show whether or not something is independent. And the way we do that is we compare the marginal distribution to the conditional distribution. And it wouldn't matter if we did sports given you were a boy or a girl, they would both be different. And for boys, it would be much higher. In fact, for boys, it would be 60 out of 227. So let me put that on the calculator real quick. So 60 divided by 227, which is going to be much higher than the 18.8%, because remember, this would be kind of like the weighted average of those two. So 26.4% compared to 18.8. Again, there's clearly, if we look at the yellow ones here, there's a big difference between those two. All right, example 4. So all right, you have a well-shuffled standard deck of 52 cards with no jokers, so otherwise it would be 54. Find the following. All right, so these might be a little bit difficult for you, but we're going to go through them together, especially if you're not really familiar with cards. So there are 4 suits, and then there are 13 ranks. All right, so on this one card is drawn. Find the probability it's an ace or a red. So probability it's an ace. There are 4 aces out of 52, so it'll be 4 out of 52. Out of red, half the cards are red, the other half are black, so that would be 26 out of 52. But then we have to subtract the intersection of those two. So how many aces are red? Well, 2 of your aces are going to be red, the ace of diamonds and the ace of hearts. So that would be subtracting the 2 out of 52. And when we add all these fractions and then we subtract this one, what's nice is they're all out of the 52, and so they all have the same denominator. We can add or subtract them, just their numerators, and keep the denominator same. So that would give us 30 minus 2 would be 28. So we have a 28 out of 52 percent chance of getting an ace or a red card. When card is drawn, find the probability that it's numbered or a spade. So the numbered cards are going to be 2 through 9, or 2 through 10. So there are 9 of them, 9 ranks of them at least, and then 4 suits altogether. So it'll be 36 out of 52. You could also think of your face cards, or 3 face cards, and then an ace would be 4. 4 times 4 would be 16. So there are 16 cards that we're not concerned with, which would be, we could subtract that from 52 to give you 36. All right, and a spade is going to be 1 out of the 4 suits, so that's going to be 13 out of 52. And then how many of them are numbered spades? Well, there are 9 ranks that are numbered, and so there would be 9 that are ranked 9 numbered spades. So we subtract those 9s because they got counted twice. So that would really just be like 4 more than this, which would be 40 out of 52. One card's drawn, find the probability that it is a jack, king, or queen, or red, but not both. Not both means we're going to subtract it twice, so we're really only interested in the ones that are only a jack, king, or queen, or only red, but not both. So we got to subtract it twice. All right, so jack, king, and queens, that's 3 ranks times 4 suits, which would give you 12, and then probability to red is half. But how many of them are Jack, Kings, and Queens that are red? Well, half of those would be red because the other half would be black, because half of them are hearts and diamonds, the other half are spades and clubs. So that'd be 2 times 6, 6 over 52, which would be 12. So we're subtracting 12, and we end up just with the 26 out of 52. All right, so if you find this kind of difficult, don't worry, I'm pretty sure there's not going to be any questions specifically about cards where you'd have to know what is in a deck of cards, even though I don't think it's like that hard to do. You probably know it, but there won't be anything like that on the test. So if you're not that familiar with cards, it's not the end of the world. But all right, one card is drawn. Find the probability that it is a heart or a Jack, King, or Queen. Well, the hearts are going to be 13. There are 13 of them because there's 13 ranks. And then Jack, King, or Queens are going to be 3. So that's 3 ranks times 4 suits would be 12. And then we're going to subtract those that are Jack, Kings, and Queens of hearts, which there are 3 of them. So that's going to give us 9 plus that would be 22 out of 52. One card is drawn. Find the probability it's red or a club. So red cards would be half of them. The clubs would be a third or a fourth of them. And then there are no red clubs because the clubs are all black cards, right? The only red cards are going to be the diamonds or the hearts. So there's no intersection. Those two are actually mutually exclusive. So kind of in that example, we wouldn't even need to use the general rule. We could use just our addition rule because they're mutually exclusive. So when they're mutually exclusive, just add them together, which would give us obviously 3/4 of the cards. The only cards that we're not interested in are the ones that are spades, right? So one card is drawn. Find the probability that's a red or a heart, but not both. So if we're doing not both, then that means we're doing an exclusive OR, which means that we're actually going to end up multiplying this by 2. So that's what I did wrong here. So the intersection of the 2 gets multiplied by 2. All right, so we have 26. Half of them are going to be red. A fourth of them are going to be hearts. And then all the hearts are red, so the intersection is also 13 out of 52. When we multiply that by 2, we get 26, so we're left with just the 13 out of 52. So looks like I did it right. I just forgot to, I just forgot to mark the fact that we were doubling it. All right, which should make sense because if we're interested in red cards or heart cards, but not red heart cards, well, that would eliminate all the heart cards. So we're really just interested in the diamonds, which is 1/4. So it actually is working itself out. All right, number 1, pet ownership. So this one is in the back of the book because it is numbered 1. Suppose 25% of people have a dog, 29% have a cat, 12% have both. So if you want to fill in the Venn diagram, which I recommend, well, again, I did 25 and 29 straddling the line so we know that it includes the overlap. And if I want to know the disjoint probability of only having a dog but not a cat, we'd subtract these two, giving me 13%, subtract these two, yielding 17%. Now I can add all 3 of the disjoint probabilities in order to find out the probability of having a dog or a cat, or both, right, which is the inclusive OR. The other way you could do it is by adding the 2 probabilities together, then subtracting the overlap, the 12% that had both, that got counted twice. So probability of having a dog or a cat, that would be, you can also do 25% plus a 17 if you want, which would be 42%. So 42%, or you can add all 3, lots of different ways to do it. Neither, so it'd be 1 minus 42%, which would be 58. So out here somewhere we'd have 58% that don't have a cat or a dog. A dog but no cat. So dog but no cat, that'll be 13%, right? A dog or a cat but not both. So that's going to be the disjoint ones. We'd subtract the 12% twice from both of these, which would give us 30%. Or you can add the 13 and the 17, still get 30%. Kind of cool. All right, workers. Employment data at a large company reveals 72% of the workers are married, 44 are college grads, and that half of the college grads are married. Okay, so if 44 are college grads, half of them married would be 22%. Okay, so that's the first thing I have to solve for. And I did the overall probabilities there, and then if I subtracted it, that would mean that 22% are graduates. Obviously, that's why they said it was half. Half of those are married, you got it, and then subtracting those two would give us 50% are married but are not college graduates. So that's our Venn diagram. We could also add these all together, which would give us 94. That would give us 6% on the outside. All right, neither married nor a college grad. So that, like I said, that was 6% on the outside. Married but not a college grad would be 50%. married or college grad, so add up all three of these together, or do one minus that, we already kind of did before, or add those two, then subtract the 22% that was overlapped. So lots of different ways, 94%. Cards. Okay, so this one's going to be challenging. It's going to make you think a little bit, but it's good for you. These are all conditional probabilities. So we have to remember our rule for conditional probabilities. We have the intersection of both occurring divided by the probability of event A, which was the one that we were told happened. So that's going to be our new denominator. So what's the probability it's a heart given that it's red? So how many red cards do we have? That's going to be half of them, 26. Technically, these should both be probabilities, so it should be 26 out of 52, and the numerator should be something out of 52 as well. But when you have a same numerator or denominator in both the numerator and denominator, they kind of undo each other, and so you can just simplify it like this. Probability to heart, that's going to be 13 out of those 26. So of the 26 red cards, what percent are hearts and red? That's going to be 13. So 13 out of 26 is 1/2, right? Basically, hearts are going to be half of your red because the other half are going to be the diamonds, and that should make sense, right? All right, how many cards do we have that are red and hearts? Well, okay, so given it's a heart, basically, what's probably it's red given it's a heart? Well, you should be able to think about that for a second. So hearts, of all the hearts, that's going to be 13, and how many cards are red and hearts? That's 13. So all 13 out of 13, which is probability 1. So shouldn't be that tough. Just be careful. Remember, it's not 26 in the numerator. It's the intersection of the two, right? Not the probability of red divided by the probability of heart. That's not what we're doing here. That's a common misconception. All right, ace divided by red. So of all the red cards, which is 26, what are aces and reds? So red aces would be 2 of them, right? Because you've got the diamond and the heart. So that would be 1 out of 13, or about 7.7%. I think there was a typo on this if I printed it out, but you guys are watching the videos, so you have a new version, so you don't have to worry about the typo. All right, probability of queen given a face card. So all the face cards would be 12, and then of the face cards, how many of them are queens? So basically, queen face cards would be 3 of them, or sorry, 4 of them. So 4 out of 12, which would be 1/3 essentially. All right. All right, 25. I think this might be the last one we're doing. Yeah, last one. Okay, almost there. Kind of a shorter, and we started a new unit, so good stuff. Our new chapter. You're dealt a hand of 3 cards, one at a time without replacement. Okay, so that means that this is no longer going to be independent, like rolling a dice, where one event occurring doesn't change the likelihood of the other. So our denominators are going to change on every one of these. You'll notice that trend, okay, because it's without replacement. All right, find the probability of each of the following. Your first heart you get is the 3rd card dealt. So that means the first 2 cards can't be hearts, which would be the first card dealt would be 39 out of 52, because there are 39 that are not hearts, right? And then after that, there's only 38 remaining that are not hearts. And then the third one has to be a heart, which there's still 13 of those in the deck. So this would be 39 out of 52 times 38 out of 51 times 13 out of 50. And the reason the denominators go down 1 each time, because there's 1 less card, and the reason we go down from 39 to 38, because we've already drawn 1 that was non-heart, so there's only 38 non-hearts left. All right, so I'm going to put this in the calculator. I'm going to do it as a fraction and then convert it to a decimal. So it's clear, you have clear entry. You can see what you're putting in. So 38 times 13, otherwise parentheses and stuff can mess you up. 52 times 51 times 50. All right, so that's going to be that fraction. I'm going to convert this to a decimal, so I'm going to go to math, the second option, which is decimal, and that'll give it to me as a decimal. Okay, cool. All right, what's the probability all 3 of them are red? That is, all of them are diamonds or heart. Okay, so that's the first one would be half the deck, 26. And then once we've removed 1 of them, there's only 25 out of 51 remaining, and then 24 out of 50 remaining. And so I'm actually going to go up here and edit this one, because all it's changing is the numerator, and I'm lazy. All right, so 26, 25, 24. Okay, and then we can change that to a decimal. All right, got it. Okay, and then no spades. All right, so spades are going to be 13, so that would be 39, and then 38 and 37, because it's staying the same. We're asking for the same thing each time, is what I meant by that. Ready? Which actually you could go up to this one because it's even more similar to it. And then change that 37. Okay. Math, convert to a decimal, 41 point. Okay, I rounded. All right, at least one ace. So anytime we have at least one, that means you could have one ace exactly out of 3, 2 aces out of 3, or very unrare, very unlikely, very rare, 3 aces in a row. And we don't want to find those individual probabilities. It gets to be a mess. So instead, let's find the probability using the complement. So let's find the likelihood that you don't get an ace at all, and then subtract it from 1. And that'll leave us the other possible branches on the tree. All right, so probability the first one's not an ace is, well, there's only 4 aces, right? So that would be 48 other cards out of 52, and then 47 out of 51, and then 46 out of 50. And I'm going to subtract that from 1. Don't forget that important step. So going back up here. So we're going to do 48, 47, 46, and then you can go ahead and convert it to a decimal, I suppose, if you want to. So math, decimal. All right, then I'm going to do 1 minus, then arrow up, and paste that. All right, so got it, 21.17. All right, that's it, about 26 minutes or so, not too bad. Let me know if you have any questions, and I'll see you guys later.